My name is Jasmine S. Puluran from Group 1 and I will report about intelligent materials. So, normal materials have limited responses. Intelligent materials have appropriate responses in the same every time. Intelligent response to stimulus with one predictable action. So, intelligent materials are materials that have to respond to stimuli and environmental changes and to activate their functions according to these changes. The stimuli like temperature, pressure, electric flow, magnetic flow, light, mechanical, etc. can originate internally or externally. Currently, many scientists are studying the structure of natural materials and using them as models in their own research, simply because these structures possess such sought-after properties as strength, lightness, and elasticity. One of the scientists is Galgan Akbaba. So, Galgan Akbaba is a member of the Turkish Bilim ve Teknik or Science and Technology Magazine Research and Publication Group. He speaks of the superior characteristics of natural materials and the ways in which we can make use of them. So, one of the scientists is Ilhan Aksay. So, he turned his thoughts to wondering how we might produce better, stronger, useful, and functional ceramics. To produce ceramics, temperatures greater than 1000 to 1500 Celsius are generally needed. Notice the extraordinary properties of abalone shells. Aksay developed some very hard, resistant ceramic metal composites because he was inspired by those models. A boron carbide or aluminum composite he helped develop was used as armor plating for tanks. In order to produce biomedic materials, today scientists are carrying out research at the microscopic level. As one example, Professor Aksay points out that the bioceramic type materials in bones and teeth are formed at body temperature with a combination of organic materials such as proteins and yet possess properties much superior to those of man-made ceramics. Extraordinary properties of abalone shell. So it magnified 300,000 times with an electron microscope. It resembled a brick wall with calcium carbonate bricks alternating with a protein mortar. Extremely strong due to its laminated structure and less brittle than man-made ceramics. The abalone shell inspired by such models, Aksay developed a very hard resistant metallic ceramic of aluminum boron carbide material. After being tested in various US Army laboratories, this material was used as armor plating for tanks. So this is an example of what abalone shell looks like. Composite materials. These are solid materials that result when two or more substances are combined to form a new substance possessing properties that are superior to those of the original ingredients. Light composite materials are used in a wide number of purposes from space technology to sports equipment. Composite materials are generally used for buildings, bridges, and other structures. So, fiberglass, used in boat, hulls, fishing rods, and sport equipment materials such as bows and arrows. It is created by mixing fine glass fibers with a jelly-like plastic called polymer. It is a composite consisting of graphite and carbon fibers are among the 10 best engineering discoveries of the last 25 years. These are the examples of work and fiberglass use. For example, a racing car, a yacht, spacecraft, and other more. Fiberglass technology in crocodile skin. It began to be used in 20th century, has existed in living things since the day of their creation. Carbon fibers can also be equivalent in contrast with collagen protein fibers in crocodile skin. Since crocodiles are cold-blooded, their skin, which is collagen protected, is heat resistant, same as aircrafts and tanks. And that's all my report.
My name is Roxa Vilmara Villanueva, and I will be discussing steel cable technology in muscles. Another example of natural composites are tendons. These tissues, which connect muscles to the bones, have a very firm yet pliant structure, thanks to the collagen-based fibers that make them up. In fact, the steel cable technology used in present-day suspension bridges was inspired by the structure of tendons in the human body. Next is the multi-purpose whale blubber. A layer of fat covers the bodies of dolphins and whales, serving as a natural flotation mechanism that allows whales to rise to the surface to breathe. At the same time, it protects these warm-blooded mammals from the cold water of the ocean depths. Another property of whale blubber is that when metabolized, it provides 2 to 3 times as much energy as sugar or protein. During a whale's non-feeding migration of thousands of kilometers, when it is unable to find sufficient food, it obtains the needed energy from this fat in its body. Alongside this, whale blubber is a very flexible rubber-like material. Every time it beats its tail in the water, the elastic recoil of blubber is compressed and stretched. This not only provides the whale with extra speed, but also allows a 20% energy saving on long journeys. With all these properties, whale blubber is regarded as a substance with the very widest range of functions. Next is the mother of pearl special damage limiting structure. The nacre structure making up the inner layers of a mollusk shell has been imitated in the development of materials for use in super tough jet engine blades. Some 95% of the mother of pearl consists of chalk. Yes, thanks to its composite structure, it is 3,000 times tougher than bulk chalk. When examined under the microscope, microscopic platelets 8 micrometers across and 0.5 micrometers thick can be seen. These platelets are composed of a dense and crystalline form of calcium carbonate, yet they can be joined together, thanks to a sticky-like protein. This combination provides toughness in 2 ways. When mother of pearl is stressed by a heavy load, any cracks that form begin to spread, but change direction as they attempt to pass through the protein layers. This disperses the force imposed, thus preventing fractures. A second strengthening factor is that whenever a crack does form, the protein layers stretch out into strands across the fracture, absorbing the energy that would permit the cracks to continue. The internal structure of mother of pearl resembles a brick wall and consists of platelets held together with organic mortar. Cracks caused by impacts change direction as they attempt to pass through this mortar, which stops them in their tracks. Next is the hardness of wood is hidden in its design. Wood's hard resistance structure derives from producing this cellulose, a hard material that is not soluble in water. This property of cellulose makes wood so versatile in construction. Described as tension-bearing and matchless, cellulose is used much more extensively than other building materials in buildings, bridges, furniture, and any number of items. Because wood absorbs the energy from low-velocity impacts, it's highly effective at restricting damage to one specific location. In particular, the damage is reduced the most when the impact occurs at right angles to the direction of the grain. Diagnostic research has shown that different types of wood exhibit different levels of resistance. One of the factors is density, since denser woods absorb more energy during impact. Last is spider silk is stronger than steel. According to scientists, spider thread is one of the strongest materials known. If we set down all of a spider web's characteristics, the resulting list will be a very long one. Yet even just a few examples of the properties of spider silk are enough to make the point. This silk thread spun by spiders measuring just 1,000th of a millimeter across is 5 times stronger than steel of the same thickness. It can stretch up to 4 times its own length, and it is also so light that enough thread to stretch clear around the planet would weigh only 320 grams.
I'm Yon Andre Lopez, and I'm here to discuss about intelligence materials, specifically about spider silks. Spider silk is a protein fiber spun by spiders. It has 5 different types for different uses. The first one is the ampullate major silk, the capture spiral silk, the tubuliform silk, aciniform silk, and the ampullate minor silk. Some facts about spider silk. Spider silk has a gazillion of uses. Gazillion meaning it has a lot of uses. Some spiders eat their own silk. Spiders can make webs in different shapes. Not all spiders can spin webs. Humans have not been able to replicate spider silk. There's a spider that spins golden silks. There's even a spider that spins its web underwater. And some spiders use the silk to create decoys. The ampullate major silk. It is also known as the dragline silk. It is used for the web's outer rim and spokes and the lifeline. The ampullate minor silk. It is used for the temporary scaffolding during the web construction. The capture spiral silk. It is also known as the flagelliform silk, used for the capturing lines of the web. It is like the pattern or the template of the web being made by the spiders. The tubuliform silk. It is also known as the egg cocoon silk. It is used for protective egg sacs. So, when compared to the chickens, the tubuliform silk is the shell of the egg that covers the spiderlings or the offspring of the spiders. Aciniform silk. It is used to wrap and secure freshly captured prey. It is used in the male sperm webs and used in the stabilimenta. It is what the spider are using when they are about to eat their prey. So this is the summary of the spider webs, different type of spider webs or spider silks. Different uses of spider silk. First, it can be used as a bandage. It can be also used as a fishing line, a bulletproof vest, because it is considered that spider silk is stronger than steel. So, if it's stronger than steel, then it can be used as a bulletproof vest. Of course, it can be used to make clothes, and it can be used also as artificial tendons. Technology in nature. Phil Gates. Phil Gates is a well-known scientist and author of the Wild Book technology. It states that many of our best inventions are copied from or already in use by other living things. So it is said that our invention is like not really an invention. It's more of a replicate of what the other living things are already using in their normal lives.
Good day, sir. I'm Emmanuel Obulantad, a civil engineering student sa Engineer Standing. So here's my report. First, the Eider duct and its insulation system. The Eider duct employs insulation and uses its feather to protect eggs and featherless chicks from cold air by keeping it warm. This is the same as wearing layers of clothing to keep us warm. So itong Eider duct na to ay commonly found sa Northern Sea na kung saan nakapag-survive sila sa cold temperature dito dahil sa kanilang thick feathers at ginagamit nila ito to protect their eggs. Next is fiber optic technology in living creatures. Fiber optics are transparent glass cables capable of transmitting light, can be easily bent and twisted. They can pipe light into even the most inaccessible locations. Possess the advantage of being able to carry coded messages loaded onto them, much better than other cables can. The polar bear's fur is very similar to an optical fiber, carrying the rays of the faint polar sun directly to the animal's body. So itong fiber optic na to para sa ating mga tao ay very useful dahil nagagamit natin ito for broadcasting and para sa mga computer networks. Next is Arctic birds using counter-current heat exchangers. In the coldest climates, local birds generally have their feet either cold water or standing on ice, but they are not freezing because they possess circulatory systems that reduce heat loss to a minimum. This natural heat exchange mechanism, known as a counter current, is the same as that used in various machines. So, may mga local birds na kayang magtagal sa mga cold water or sa mga ice dahil sa kanilang feet na made up of tendons or bones. Ang example ng uri ng birds na to ay rough-legged hawk and snowy owl. Next is, can plants use an electrical switch? The carnivorous bean's flytrap catches insects that land on its hinged trunk and trigger the hairs on it. These hairs act like electrical switches. The instant one is touched, it gives off electrical signals that change the water balance in the plant cells and trigger the flow of water out of cells along the leaf midrib closing the trap. The switches controlling the flow of current in electrical circuits to operate in much the way. So may video akong hinanda kung paano nanguhuli ang isang carnivorous Venus flytrap. Once natapak ang prey is sa triggered hairs ng carnivorous Venus flytrap is automatically mag-close agad ang kanilang trap. Next is, if nerve cells lack insulation, nerve fibers carry messages from the brain to the muscle and other organs, and from there, message back to the brain. So, kapag hindi present ang nerve fibers, may maglilik na electrical signals into the surrounding tissues na magagarbling sa message ng nadala-dala ng nerve fibers or magkakaroon ng damage siya sa specific part ng ating katawan. Next is fairy dogs ventilation technology. Many animals build underground shelters that require special features to defend them from predators. Ang fairy dogs ay natawag na ground squirrel or burrowing rodent. So, para makapagtago sila sa mga predators is nag-ukay sila pa ilalim sa lupa. Mas malalim na hukay is mas safer sila doon. So, may video akong hinanda on how they live in underground. Next is WAPs and the paper industry. A series of chemical processes turn logs of wood into a kind of pulp that can later be made into paper. However, the natural inventors of paper are actually WAPs. To build their nest, WAPs use paper that they make by mixing their saliva with shreds of chewed wood. Our furniture industry makes chipboard in exactly the same way, although using glue instead of saliva. So itong WAPs na to ay benefit rin sa ating mga tao dahil they eat crop destroying bugs such as caterpillars, grubs, and weevils. Also, they help pollinate plants because of their hairy legs. Next, a robotic arm inspired by the elephant's trunk. A scientist tried to design a robotic arm. One of the worst problem they faced was achieving freedom of movement. In order for a robot arms to serve any useful purpose, it must be able to perform all movements required by the particular task. One robotic arm constructed in the US at Rice University clearly reveals the elephant trunk's superior design. There is no single skeleton-like structure in the trunk, thus endowing it with the enormous flexibility and lightness. The robotic arm, on the other hand, does have a spine. So, unlike sa elephant trunk, na maaring igalaw yung trunk in any direction, dito sa robotic arm ay na-construct lang sa 32 degrees of movement freedom. So, that's all. Thank you for listening and God bless.
I'm Jason G. Perlada. I'm here to report about biologically inspired mechanisms. So first, we're going to tackle about comparisons, biological materials and synthetic materials. Building blocks of the body are linked into polymers with control of stereochemistry to affect regularity in chemistry and thus higher order interactions. So, chemically and physically, these polymeric building blocks are programmed into self-organize. Along with membrane interfaces, compartmentalization helps in this process. The entire materials assembly process is governed by the interplay between genetic programs, environmental conditions inside and outside of the cells, and the remarkable specificity and control achieved through enzymic processes. Polymer assembly as the basis for structural hierarchy and function in biology is most often governed by many weak bonds. It is high frequency and location of these types of bonds that allow assembly or disassembly of these material systems within reasonable energy demands to permit functions. These processes are mediated by water structure and location with respect to organic components and features such as hydrophobic hydration play a major role in the processes. So, for the background of the silk, silks are externally spun protein fibers generated by spiders and insects. For over 5,000 years, World silkworm, or also known as Borbix murray, is used in textile industry. Spider silk's production has not been domesticated. Why? It is because they are hard to raise in large numbers due to their predatory nature. Silks are interesting because of their durability, luster, and feel. Spiders and silkworms represent the strongest natural fibers known. Silks are mechanically stable up to almost 2008 C. So when we talk about their mechanisms, silk proteins are hydrophobic based on predominance of glycine and alanine amino acids. In recent studies, micelle and gel states were identified that these are important steps governing chain silk protein interactions toward organized silk structures. These soft micelles consist of flexible molecules, and the structures can grow and change shape into response to changes in protein and concentration. So, lysotropic liquid crystalline phase behavior can help explain the assembly of silk protein polymer chains into domains of high concentration with orientation driven by micellar behavior and water efflux through channels in these structures. So, hydrophilic blocks interact with water and define micellar partitioning such as the lard N and C terminals. So, the final step of the process, the assembled proteins are spun through the abdomen of nature of silkworms. Spun fibers are insoluble in water, which means it will not be dissolved. So mimetic systems. Employing new insights into silk fiber solubility and assembly has permitted new forms of these protein-based materials to be generated. The example of this is the turkey sponge, formed from regenerated silk fibrion. Blending silk fibrion and polyethylene oxide to obtain sufficient solution viscosity suitable for electrospinning to generate nanoscale diameter fibers. So, efforts are underway in many laboratories to develop synthetic analogs of silk. So, for example, the copopolymers of glycine, alanine repeats, and the with polyethylene glycol have been studied to provide fundamental insight into control of polymer assembly and structure. With continuing advances in genetic engineering, improved quantities and the availability of additional sequence variants of silk proteins can be anticipated. So, this one can serve as a blueprint for the future designs. So when we talk about seashells, high performance organic and inorganic composites from nature, so we will just have a short background about this one. So despite the compositions of predominantly brittle inorganic salts, the shells of mollusks have been have exceptional toughness. The calcium carbonate, or what we know as chalk, comprises up to 98% of the content of many of these shells, with the remaining few percent consisting of proteins and glycoproteins. So, argonite, calite, and berylite are polymorphs of this calcium. So it is soluble or partic acid-rich glycoproteins direct cell formation by binding with calcium, leading into formation of aragonite crystals. So that is the end of my report.
I'm Patrick Chavez. My report is all about seashells, high-performance organic, inorganic, and composites from nature. Mechanism. The organic matrix of the nacreous layer in mollusk shells is flexible and contributes to the strength and toughness of the shell. Insoluble fibers bind to the aragonite tablets at the optimized inorganic interface, acting as a natural adhesive between the layers. Biomimetics. To form relatively inexpensive materials that mimic the mechanical features of nacre, which interfaces have been layered between sheets of ceramic. In this method, each layer of ceramic is approximately 200 mm thick and is cut from a larger sheet made by treating silicon carbide powder with boron to create a pliable material. Shark skin, biological approaches to efficient swimming via control of fluid dynamics. Background. Mechanism. The roughness of shark skin is paradoxical to principles of fluids dynamics since rough surfaces increase drag and shark skin pedicle just in front of the tail. However, the rough texture of shark skin reduces drag due to the presence of microscopic riblets on the surface of the skin. Biomimetics. The structure of shark skin has prompted swimsuit and wetsuit manufacturers to develop new designs to reduce drag in water to improve times for competitive swimmers or to improve navigation by scuba divers. Gecko and birds biological solutions to sticking to surfaces. Background. Gecko lizards do not have lethal suction cups on their feet but are able to climb up walls and stick to ceilings. The feet of these animals have toe pads consisting of tiny hair-like structure called setae, made of keratin. Biomimetics. New tapes, similar in design to lizard feet, have been designed and developed as a dry adhesive to eliminate the sticky residue normally left from more traditional tapes and glues. This type of gecko-like adhesive could eventually be used for a wide range of applications, from hanging tapes, tries, and rock climbing to wound closure in surgery. Muscles, efficient biological conversion of chemical energy into mechanical energy. Muscles are classified into a skeletal, often associated with bone, cardiac, found in the heart, and smooth lining of hollow organs in the gastrointestinal, urogenital, and cardiovascular systems. Mechanisms. Myosin consists of globular head with ATP and actin binding sites, and a long tail that is involved in polymerization into myosin filaments. Actin is polymerized and filaments and forms the ladder along which myosin filament climb to generate motion. Biomimetics. Muscles are natural actuators. Actuators are controllable machines that convert energy to mechanical work by means of a shape and or dimensional change. Electroactive polymers often exhibit the closest performance resemblance to biological muscle. Development of copolymer gels made of cross-linked hydrogels have resulted in actuators with improved response time and good mechanical properties. Tissue engineering is a means of creating a biological substitute that is capable of restoring, maintaining, and improving function. That's all.